Hey everybody. So we're now going to do yet another thing where we take an idea from single variable calculus, from our functions of a single variable, and expand that idea into functions of several variables. All right, so we've been looking at partial derivatives quite a bit. Let's go the other direction and think about integration. So integration, right, for single variable functions, the geometric interpretation is area. So what you might imagine, and you'd be correct, is that now we're going to be talking about volumes. So let's take a look at a graph. We'll take a look at this graph. We'll kind of get an idea of what we're going to do, and then we'll work out some of the details. And do an example of, well, you'll see, we'll get there. So here's a function, okay? Here's just some surface in, this is a z equals a function of x and y. Now, remember in single variable calculus, we want an area over an interval usually, right? We have the improper integration, but let's focus on when we have like an interval, we're looking between 2 points. Now that we've got an extra variable, we're going to be looking over a region. And we're going to start by looking at rectangular regions. So there's a region in the XY plane, right? And I want to find the volume between that region and the surface, okay? So now notice I've picked a place where our function is above the x-axis, right? And just like in your previous experience with integration, right? I'm going to mostly talk about it as if we're always dealing with positive functions in volume, but of course, you'll see when we do the computations, if you're below the x-axis, you're going to end up with negative numbers, and we don't really have a concept of negative volumes, but just like in single variable functions, that negative can represent something. For instance, you may have seen when you integrated over a velocity, if it was negative, you end up with a negative distance, meaning I was moving backwards. So we'll have the same kinds of interpretations here. But we're gonna hold off on interpretations for a little while. Let's work through the mechanics of this. So if I want the area between the XY plane, sorry, the volume between the XY plane and this surface over this region, right? In other words, so now if I look at my graph, only a portion of it lies above that little region. Like if I look from above, you see the thing that I just turned on, this little is our portion of the surface that lies precisely above that little region. So I'm going to get rid of everything else. So now we're just looking at the little piece of our surface that's above that region, right? Again, the z-axis is in blue, x is in red, and y is in green, I believe, if I'm remembering correctly. We're going to use a very similar idea that we used for coming up with integrals, right? In one dimension, we had, or with one variable, you take rectangles to approximate strange shapes, right? Well, now we don't have rectangles, we're going to have boxes, right? So for each of these squares or rectangles, I can draw a box whose height is equal to the function somewhere in that region, okay, right? And it's very similar to what happened when we did this for a single variable, in the sense that it turns out, right, remember in single variable calculus, we would take a region or an interval and divide it up and draw rectangles. And if you did this with me, I did a lot of right endpoints, but we discussed you could also do left endpoints, you could do midpoints, and it turns out it won't matter, right? So you could take the upper right corner of all of these rectangles, you could take the center for all of these rectangles. Under the correct conditions, right? Generally, continuity, you can have a few discontinuous spots. As long as they're not asymptotes and so forth, versions of jump discontinuities for these kinds of functions. As long as you don't have any extreme situations, as you do what you might expect, we can start chopping up these rectangles into smaller rectangles to get better and better approximations, right? So I've got, it's a bit hard for the computer to render now, so it won't let me move. But as you can imagine, right, we're looking now at a better approximation. In fact, let's go backwards for a second. Let's turn down our approximation, right? Here's the simplest approximation, a single cube. Its height is at the midpoint. I guess it's not a cube, a rectangular solid. Its height is at the midpoint of that rectangle in the XY plane. You take the value of the function, that's the height of it, right? That's an okay approximation, but we expect that as we add more rectangles, we're getting a better approximation, right? Rectangular solids, very, very analogous to what happened in Calc 1, right? And so you're still having this, the idea of this approximating volumes, okay? So that's our big picture, right? I'm gonna go through this once, we're eventually gonna get to how to do integration, which just like in Calc 1, if you compare to doing Riemann sums, which could be very difficult and time consuming, it's much easier once we learn, let's call them the shortcuts, though they're not necessarily shortcuts, they're just beautiful results of theory. I think it's still important to understand where that stuff comes from, right? So in this case, it's approximating rectangles. So let's work out what this is going to look like exactly, and then we'll do an example of an approximating sum. We'll do a very simple one, and then in the next video, we'll move into how do we compute these things without having to draw rectangles and so forth. Okay, let's do that now. So we'll go to a whiteboard. All right, so let's say, I'm going to try to draw that picture. It's not going to be as nice, but I want to be able to write quite a bit. So I'm going to start by drawing, I'm not going to draw the XY plane. I think that will make, I'm going to draw the axes, I should say. I think that's going to make this drawing too complicated. But let's imagine this is a region in the XY plane, right? So obviously I have to draw some number of divisions here, but of course I'm trying to just represent an arbitrary number of divisions. Let's give this region a name. Let's say we're looking at the region. So here's a notation you may not have seen. What I mean by this is the set of points x, y in R2 such that x is between A and B and y is between C and D. Okay, so maybe we'll say here's A, here's B, so x is coming positive out towards us, and here's C and D, so y is going in the positive direction to the right. Okay. So there's our little region we want to add our volume up over. So we're going to name these points. Let's start here. This will be A will be x naught, and then for each little division, right, corresponding to these hash marks in this grid, we get x1 on up. We'll call it xj, and let's go up to x sub m. Okay, so we're just looking at in fact, you know what? I'm going to redo this drawing a little bit. Let's do it a little bit differently. I've got a better idea. So this is still our region. Let's just make this whole drawing easier to look at. Let's look at the region from above, okay? So we don't have to imagine so much about what these things are representing, okay? So here we have the point here, the point on this coordinate, for instance, in the XY plane would have coordinates A, C. right? Its x coordinate, we're calling x naught. And as we divide this thing up, we're moving over by little bits, x1, x2, dot, dot, dot. We'll call it x sub I, dot, dot, dot. And we get up to x sub m, right? Which is also going to be equal to b. And in the y direction, we do the same thing. We start with y naught, right? We divide this thing up into a bunch of regions. We can call any y value in there. I'll represent an arbitrary y value as y sub I. We're just increasing by 1, y sub 2, and so on, up to y sub n, which is also d. Okay, so this is now our region with these little rectangles that we've gridded up. Okay, so I'll just draw a few grid lines so we get the idea. We're dividing this thing up into squares as in that other picture. Now, if I want to, I need to keep track of all these squares, okay? So I can call, oh, sorry, I should call this y coordinate j, okay? So I can call each square, let's see, let's call a rectangle Rij is going to be the rectangle from xi minus 1 to x sub I cross yi minus 1, sorry, j minus 1, y sub j. In other words, if, for instance, let's just do one. If I did the rectangle 2, 3, that's going to be the rectangle that goes between x1 and x2. So let's use another color. Between these two, and between y2 and y3. So that would be my square right here, right? So I'm labeling each rectangle by using the x, the sort of upper bound on the x and the upper bound on the y. And each one is going to be one of our little units, okay? So that's just for notation, what we mean by rectangle Rij, okay? So now, imagine, oh, sorry, one more piece of notation. We'll call then points x, sorry, let's need a little more space. Let's move this up here. And then the point xij star, yij star is any point in the rectangle Rij. So if I wrote x2, 3, comma y2, 3, and I'll give them both a little star, all I mean by that is pick any point in that rectangle, any interior point, right? When we actually compute these things, we might decide to take midpoints or upper right corners, but it will work out equivalently for any point in the interior, just like we can pick any point in our intervals when we do rectangles in Calc 1, okay? So again, this notation gets really, really dense, but think of that picture I started with. We're just drawing boxes from these points up to the surface, okay? So let's do that. Let's write now a little formula for the volume. Let's call it the ijth volume. And all I mean by that is I take the ijth square. I'm going to go back up to this grid up here. Let's say it's this particular square right here. Remember, all this time, there's a surface floating above this thing. Maybe it's below, but I'm going to draw it above, right? And we pick a point in this square, and we find the corresponding point when we evaluate the function. That determines then the height of the rectangle I'm going to draw. Right? Picture's not perfect, but wherever that function evaluates is the height of that rectangular box. right? That rectangular solid. So how do we figure out the volume of something like that? You take the height, which is just the function f of xij star, y of ij star, times, well, we need the width, the area of the bottom, which is just the length and width of this little rectangular little rectangle on the bottom. And this is something very familiar to us. Delta x, delta y, right? Delta x is the little change in x. Delta y is the little change in y, right? Again, in general, it doesn't matter if you keep these intervals the same width as you go on, as long as they're all shrinking eventually. But it's easiest if we just divide them up evenly for most of the kinds of integrals we do, okay? Well, we usually shorthand this delta x, delta y is just what we'll call delta area, the little piece of area on the bottom times the height. So that gives us the volume of a particular rectangular solid. So now, let's write down an expression for the volume of an approximate volume, an approximate volume, because remember what we're trying to really do here, what we're trying to really do is find the precise volume. If I drew these corners up to the surface, maybe I'll get rid of this rectangle now. If I drew corners up to the surface, wrong tool. There was my box. Corners up to the surface, right? There's going to be some kind of shape where above that thing, right? I want the volume of that box, but I'm going to approximate it with these rectangular solids. So I would take the volume of the first approximating rectangle, or rectangular solid, rectangle 1, 1 star, y 1, 1 star, delta A, plus f of x 1, 2 star, y 1, 2 star, delta A, right? So in this little picture here, it's like I'm doing this rectangle, then this rectangle. I'm just going to move across. Oh, sorry, I went up. It doesn't really matter which direction we go, but I'm changing my y index. So I'm moving up this, right? And then I'll get f, do one more, x star, this will be 1, 3, x, y star, 1, 3, dA, plus dot, dot, dot. We'll go all the way up. I'll get x1. So I'm going up to the top here till the n, that we have n squares along this road. So it'll be xn star, y1n star, dA. Then, this is still the same sum, continuing on the same row. Actually, let's not do dot, dot, dot. So let's just do plus, because the next thing we'll do is going to be x2 sub 1. y2 sub 1 star delta A, right? So we've gone up this entire row, done all these squares, then we move down to here, and then we'll start going up this row and computing the volume above each of these squares, or the approximating volume. So we get f of x2, 2 star, y2, 2 star, dA. We keep doing that. You'll go through row 3 or column 3, 4, and you keep going on and on and on until you'll get to x m n star, y m n star, dA. Right, this upper corner, right? You've gone through all the x and y indices. Okay. Now, this is of course a very, 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 very ugly thing to write down. So we can do it with, notice we're adding a whole bunch of things. So we can use summation notation. The problem is now we've got two indices changing. So we're going to need two sums. Okay? So we're going to have I equals 1 to m, that's our x values. J equals 1 to n, and we'll do f of x, I, j star, y of I, j star, delta a. Okay? So think about it. This is really nothing new. This summation says when I equals 1, do the thing in here. Maybe I'll put in an extra pair of parentheses. We can think of there being parentheses around this. When I equals 1, do the thing in here. Well, when I equals 1, it says add up, start with j equals 1, add up where we have 1, 1, then j equals 2, 1, 2, j equals 3, 1, 3. We get those indices. That's our first row here. When you've completed that, we go to the next one, then I equals 2, and on and on and on, right? You go through all the combinations of the indices and add them all up, okay? All right, so you can probably guess what we do next. We are going to take a limit, because if we make those rectangles smaller and smaller, we will say that if this limit exists, of course, this is equal to the volume, right? The limit, though, is a little more complicated. We need n and m going to infinity. Then we take this limit, I equals 1 to m, j equals 1 to n, f of x ij star y ij star delta a, okay? If that limit exists, this is the volume, okay? What we mean is that we can make, whatever the true volume is, we can make this summation as close as possible to it by taking n and m large enough, right? Technically, we could say if you given some small difference from the true volume, I can make this approximating volume less distant from that volume by taking n and m. There exists an n that I can make, there exists a number I can make n and m larger than, so that this approximating volume will be within whatever small distance you've challenged me with. We're not going to worry about the technical definition. I don't want to start getting into epsilons and deltas right now. This is what we'll call our double integral over this region. And so we have a symbol for this. We use two integrals. R represents the region that we're integrating over. Okay? F of xy dA. Okay? And so just like the integral symbol in single variable calculus represented an area, this integral represents a volume. Of course, if the volume is below the xy plane, you're going to get negative values for z, negative values for the function when you compute this sum. So it could very well be negative, and you have to interpret what that means depending on the context of the problem. If this limit exists, we'll say the function is integrable over is integrable over the region R. Okay. So a couple of things. Let's do a couple of quick examples of the meaning of this, and then we'll do an approximating sum example. So just to be clear, so for instance, if I have the function z equals, let's do 1 minus, oops, I meant to do z equals the square root 1 minus x squared. Okay. So first let's, and then I want to find the area over the region R, which is going to be equal to -1, 1, to, let's just go from 0 to 3. Okay, so let's first picture what we've got going on here, right? So first of all, let's draw our coordinate axes. All right, we'll draw it like this. Here's my x axis. Here's my y axis. And then the z-axis, of course, is going straight up. Okay, so let's just move this over, get rid of that one. Okay, so there are our 3 axes. Let's think about this function. I can manipulate this to write x squared plus z squared equals 1, which we know to be the unit circle in the xz plane, except since z is the square root, the positive square root, this is just going to be the top half of the unit circle. But since y doesn't appear in this, remember what we get is a cylinder. We can extrude this shape along the x-axis. Oops, it doesn't include that line. Let's erase that. It's just, so something like this. Picture's not perfect, of course. All right, and it'll go in this direction as well. Okay. Now, we want the volume of this thing between 1 and -1 in terms of the x values. Well, that's precisely the width of this thing. So that's the width we're going to care about. And then our x values are going to go from 0 to 3. Right, so this would be the rectangular region, right? If we put in coordinate points here, we'd have points like 1, 0, 0. This would be 1, 3, 0. Then those 2 points back there would be the same except -1s. I don't want to busy this up anymore, okay? So the volume we're looking for is, if you can imagine filling in this shape over this length of y values, right? Well, you probably see this is just a cylinder with radius 1, except we're cutting it in half, and the volume of this cylinder is just pi r squared times the height. And from the picture, the height is 3, so this volume is just pi. R is 1, so r squared is 1, and the height is 3, so the volume is 3 pi, right? But of course, we only want half of that. So what we might write, if we were asked to compute the double integral over the region R of the function 1 minus x squared dA, right? This means the volume between the xy plane and this curve over the region R as defined up here, it's going to be half of this volume, or 3/2 pi. Right? So just like in single variable calculus, when you first learn integrals, we usually try out some ones that can be computed by simple areas. This is an example of that, right? That we're going to have to come up with other methods. But when they do fall into shapes we already know how to compute, we don't need to go through a big integral process. We can simply compute the area or the volume with whatever geometric tools we have if they apply. Okay, let's do one more thing. Let's do an example of approximating under a curve. So let's take a look at a different, one second, let's open this up. Yeah, all right, so here is a surface. Oops, sorry, I have to change. Sorry about that. Let me change to my whole desktop. That should work. Okay, sorry about that. So here's a surface graphed. Okay, this is the function. Let's write this down, and we'll get a better picture of it. So this is the function f of xy is equal to x times y. And I want to find or approximate the area over the region R is equal to the set, what did I choose? Between 2 and 3 in the x values and 1 and 4 in our y values, okay? So let's go ahead and take a look at what that might look like. So first, I'm going to bring up that region floating there on the xy plane. So I want a piece of this surface. I want to imagine the volume between this region R, it's just a little strip, and my function. So here's the part of the function that's above that, right? If we look down, we see that they match up. So we've got this bit of function above it, this oddly shaped kind of warped thing. Let's get rid of the rest of the function, right? And so what we're trying to do is find the volume between the XY plane and this twisting kind of, it's like a twisted sheet of paper or something, right? And so we're going to do it with approximating rectangles. And I'm just going to do a simple one here with 3 approximating rectangles, because those are rectangular solids, because those 3 things are going to look, are going to give us a reasonable approximation to this, right? So what does that mean? So if we're looking at, I'm going to use midpoints of these squares to do it as well. So let's start by drawing the region in the XY plane. So if it's 1, 2, 3, 1, 2, 3, 4, 5. So we're going from, here's our region. And I'm going to just split it up into unit squares, right? So I'm doing a very basic approximation. If I wanted to do better, I would maybe divide it up into, 4 or 5 intervals between 1, 2, and 3, and a few more, 10 or 12 intervals between 1 and 4. We're just going to do a simple one. And I'm going to pick the midpoints of each of these squares, right? We could pick any points. I could pick the upper right-hand points, but I'm going to pick the midpoints, which gives me the points. Let's see, it's red. So this is going to be 5 halves, 3 halves is that point. Then we're going to have 5 halves, 5 halves, and then we're going to have 5 halves, 7 halves. Right? Those are our 3 coordinates for each of these points in the XY plane. So now, our approximating volume, we will take the height of this first approximating point, f of 5 halves, 3 halves, times dA, plus f of 5 halves, 5 halves, delta A, excuse me, plus f of 5 halves, 7 halves, delta A. Well, delta A, remember, is delta x times delta y, and the way I've chosen it, they're both 1, so these just become 1s. Sorry, this volume should be approximate. So what are we going to get? F of 5 halves, 3 halves is just the product of these. 5 halves times 3 halves times 1, plus 5 halves times 5 halves times 1, plus 5 halves times 7 halves times 1. So we get 15 halves, 15 fourths. Plus 25 fourths plus 35 fourths. And so we have 40, 75 fourths as our approximating volume. Okay. Okay. I know that's a lot, and this part so far is really just about getting our intuition behind what these new double integrals mean. It is just now a volume instead of an area, and we're approximating it with these rectangular solids, right? You can look and see in this picture, in this particular one, we see it's probably a decent approximation. It misses some area under there, between these rectangles in the curve, but it also over approximates in some parts. Looks like more or less the same, so I'm going to guess that's pretty close. But we will be able to compute this volume exactly in another couple of videos. Okay, that is it for this one. Thanks, everybody. I will see you next time.